Hi everyone, my name's Max. I'm going to be presenting some work on plan relaxation. So very broadly speaking, plan relaxation is the process of relaxing a classical plan, which is a sequence of ground actions, into what we've called a partial plan. Now a partial plan specifies which actions need to be executed, but it doesn't completely specify their ordering or their variable bindings. Instead, it provides a constraint formula which defines the allowable combinations of orderings and variable bindings. So you can think of a partial plan as being a compact set of a whole set of classical plans which all achieve the same goal. So this is quite useful because at execution time, when you're executing a plan, you might say, for example, get halfway through your plan and find that for some reason it's no longer progressible. So a partial plan will provide you with a whole set of alternative ways of achieving your goal. Now this additional flexibility unfortunately comes with a computational overhead. And the problem is that finding a classical plan which satisfies these ordering and binding constraints is an NP-complete problem. So then the question we're trying to answer here is, how can you relax a classical plan into a tractable partial plan? So we're going to use the idea of tree width to define some islands of tractability within the space of partial plans. And then I'll introduce an algorithm called MKTR, which relaxes a classical plan into a tractable partial plan. And then we've done an experimental comparison with MKTR with the PRF algorithm, which is a kind of a standard deordering algorithm. So there's a lot of work which has been done on relaxing the ordering of a plan. Not so much work has been put into relaxing the variable bindings. So here's an example which I hope will show you why this can be a useful thing. So this example is taken from the barman domain, which is a standard IPC domain, where there's a robotic barman which makes drinks out of ingredients using hands and shot glasses and shakers and things. So plan P1 here achieves the goal of a shot glass containing a cocktail. Now over the first few steps, the barman picks up, what does it do? So the first few steps it pours ingredient 1 into a shot glass, and then from shot glass into a shaker. And then over the next few steps, it does the same thing with ingredient 2. And then puts down the shot glass, picks up the shaker and shakes it, pours it back into the glass, and that achieves the goal. Now, what might happen when you're executing this plan is you could get to step 2, and you might reach for ingredient 1 and find that for some reason it's not available. So what you'd like to do, in this case, is to kind of skip forward and pour ingredient 2 first instead, and then go back to ingredient 1 later once it becomes available. Now, unfortunately, you can't do this because this plan can't actually be reordered at all. And the culprit is these two operators here, the pour to clean shaker and pour to used shaker. And as the names suggest, you have to do the pour to clean shaker first. Now, it's quite easy to actually get around this problem by rebinding the actions rather than reordering it. So what I've done here in plan P2, so marked in red, we've swapped every instance of ingredient 1 with ingredient 2 and vice versa. So that now means that first of all the agent pours ingredient 2, then it goes and pours ingredient 1, and that achieves the goal. So we can achieve a kind of an equivalent reordering just by changing the variable bindings. Now, don't have to stop there. We could also swap the hands over. So in this case, swap the left hand and the right hand. You could also make use of resources which weren't even in the original plan in the first place. So if you had some, mythical 4-armed barman, you could use hands 3 and 4 in place of the left hand and the right hand, for example. What you can also do is, if you do a careful rebinding, you can actually produce a plan which can be reordered in ways that you couldn't reorder in the original plan. So in this case, I've kind of shuffled the hands around a little bit. And those two operators marked in red, grasp and drop, you can see in plan 2 they've now been flipped in their order. So yeah, so new rebindings can also create new reorderings. So we can look a bit more carefully at a partial plan. So again, I'll do this in the context of a simple example from the barman domain. So in this case, in the initial state, the hands are empty, the shot glass is clean and it's on the table, and the goal is for the shot just to contain an ingredient. So a solution to this is the simple classical plan, which I've got up there, grasp and then fill. So in the first step, you pick up the shot glass with your left hand, and in the second step, you pour the ingredient into it with your right hand. So a partial plan, the one that I've got here, is a kind of a more flexible solution to that problem. So on the left, we've got a set of schematized operators. So what I've done there is to essentially take those two actions from the classical plan and replace all the constants with variables. So you can see left hand has been replaced with h1. And then on the right-hand side, we've got a set of constraints. So the constraints do a number of things. They define an ordering of the actions, so grasp has to precede fill. They define the variable domains, so that's just saying that, for example, h1 has to be bound to either the left hand or to the right hand. It also defines the causal links, so that's saying that the hand that you use to pick up the shot glass in the first action has to be the same hand that you use to hold it in the second action. It also does some threat protection. Now it's a bit more complex, but what this is really saying when we say h1 doesn't equal h2, we're saying that whichever hand you use to hold the shot glass can't be the same hand that you use to pour it. Right. Okay, so taken all together, these constraints enforce the validity of the partial plan. So this means that any classical plan that satisfies these constraints is also valid. So it's executable and it achieves the goal. These constraints are also a minimum relaxation. So they place as few constraints on the orderings and the bindings as you can possibly do while remaining valid. So a minimum relaxation is a useful idea because what you're defining is the most flexible or the most relaxed the partial plan can be. Now, interestingly enough, you can actually find these minimum relaxations in polynomial time. So this is unlike the equivalent problem of, say, deordering, where that's an NP-complete problem. Now, this is polynomial because of the expressiveness of the language that we use to express constraints. So the language is so expressive, you can actually just directly define a constraint formula, which is the kind of the minimum relaxation. Now, I won't go into the details of how we do this, but we use a thing called the modal truth criterion, which can be just simply expressed as a constraint formula. So there's more details about that in the paper if you want to go and look at all the maths. Now, as I mentioned earlier, this extra expressiveness comes with a computational cost. So finding an instantiation of a partial plan, no matter how flexible it is an NP-complete problem. So being able to express these really flexible plans isn't actually any great benefit. But all isn't lost. We can use the idea of tree width to define islands of tractability. So tree width, very roughly speaking, it's a measure of a graph which defines kind of how cyclic a graph is. So a tree, which has no cycles at all, has a tree width of 1. A clique of, say, k vertices, so that's a complete graph where every node is connected to every other node, that has a tree width of k minus 1. It's a useful measure because a lot of NP-complete problems are actually solvable in, say, time n to the k, when the tree width of the graph is bounded by k. And then this same idea often gets applied in other NP-complete problems. And you do this by trying to find a kind of an underlying structure to your problem, which can be expressed as a graph. So that's what we're going to do here. So we're going to look at the underlying structure of a partial plan, which in this case is known as the primal graph. So it's quite a simple idea. The primal graph is a graph, and the vertices in the graph are the operators and the variables which appear in the partial plan. The graph connects two vertices if they appear in some clause in the constraint formula. So in this example, which is the same one as we had before, how do I do this? Yep, this one here. We've got the clause grasp precedes fill. So in the graph below, we've got a connection between the node grasp and fill. Now in this case, this primal graph has a tree width of 1, which means that partial plan could be instantiated in linear time. So the overall point is that a partial plan's primal graph, if it has a tree width of k, you can instantiate it in time into the k. There's proofs of that in the paper. Obviously, I won't go into it here. So what we're actually looking for then, after all this, is a minimal k tree width relaxation of a classical plan. So this is a partial plan which can't be relaxed any further without either becoming invalid or without its tree width going above some parameter k. And we've got an algorithm, which I've called MKTR, which finds these minimal k tree width relaxations. So the parameters to this algorithm are a classical plan and the maximum tree width you're willing to put up with, which is a value k greater than 0. So for example, if you were to set the tree width to set k to 2, that means that it could be, the final partial plan could be instantiated in quadratic time. So it's likely to be suitable for real-time usage. You can set the tree width higher if you like. This is likely to produce partial plans which are more flexible because you have more options in the kinds of constraints you can express. But of course that comes at a greater computational cost and possibly more time spent at runtime. So the algorithm, MKTR, it works by relaxing the causal structure of a plan, and I'll give you an example of how it works. So this is that same plan from before, the simple two-action plan, which where you pick up a shot glass and then you pour some booze into it. The first thing we do is to turn this into a causal structure. Now on the left-hand side of the graph, S0 here, we've got the initial state, and on the right-hand side, we've got the goal state. At the top, there's the grasp action. On the bottom, there's the fill action, and you can see the preconditions and the postconditions in these two columns. The arrows indicate causal links. So there's a precondition to grasp, which is that the left hand must be empty. So that's why there's an arrow going from empty left hand back to the initial state where the left hand is empty. So we can say that that precondition is kind of satisfied by that fact of the initial state. Now the first step of the algorithm is to schematize the whole thing. So as I've marked in red there, we've replaced all the constants with variables. And we've then constructed a constraint formula down here, where all the constraint formula is doing really is insisting that every variable be bound to the constant which it replaced. So in grasp, we've replaced left hand with the variable h1, and then the constraint formula says h1 must be bound to the left hand. Now we begin the process of relaxing this thing. So I've marked in red here. What we do is select some precondition of some action, and then we add in another optional causal link. So previously we were saying that h1 had to be bound to the left hand, so you had to use your left hand to pick up the shot glass. Now we're saying, well, it can be bound to the left hand or the right hand. So we add in this causal link, and we update the constraint formula. So marked in red again, we've got h1 equals left hand or h1 equals right hand. We've also had to add in this little threat protection thing at the bottom, that h1 doesn't equal h2. This is just to make sure that you don't try and use the same hand to pick up the shot glass and also pour the drink later on. We then compute the tree width of that constraint formula, which in this case is 1. So we can then do another one. So the next step, we might relax this precondition, that h2 is empty. So again, before it was bound to the right hand, and now we're going to add in another option and say, well, it could also be bound to the left hand if we want. We then update the constraint formula again, and we compute the tree width, which in this case is 2. Now, say we had a maximum tree width of 1 in this case, and of course, what we've done here is produce a partial plan with a tree width of 2. Well, in that case, we'd have to remove that option and backtrack to the previous step and try another one. So the MKTR algorithm just iteratively relaxes the causal structure in this way. It keeps on going until either the plan can't be relaxed any further, or until it's, any relaxation would push its tree width above whatever you've decided is your acceptable limit. Right, so we have compared, we've evaluated MKTR over 80 classical plans, which have been taken from 6 standard IPC domains, and we tested it with tree widths of 2 and 5, and with the time limit of 1 hour. And we compared them with the partial plans produced by the standard PRF deordering algorithm. So it was actually quite difficult to do any kind of direct comparison of the instantiations that the two techniques find. It was just infeasible. But what we can do is kind of do a set-wise comparison of the two sets of instantiations instead. So for example, we can say that, well, PRF found a subset or a superset or something of MKTR. So we found that in all cases, MKTR found all of the deorderings which are found by PRF. So that means that it never did any worse than just doing a straight deordering. So it kind of at least met that baseline requirement. Now, depending on the domain, MKTR is also able to find additional instantiations which have different variable bindings. So whereas PRF can only find reorderings, what MKTR is finding is reorderings which also make use of different variables or different resources. So in the Barman domain, for example, roughly 70% of the cases it's able to find these rebindings. So child snack did pretty well, 93%. But there are 2 domains, the parking and the scanalizer domain, where both algorithms did particularly badly. In fact, I don't think either one of them was able to find any kind of relaxation at all. In 6 cases, interestingly enough, MKTR was actually able to find reorderings which PRF could not find. So that goes back to the point I made earlier on, that by rebinding variables, sometimes that gives you more options for reordering. And in the grid visit all domain, PRF wasn't able to reorder it at all, but MKTR is able to find alternatives with different variable bindings. So MKTR 2 and 5 represent the results of using a tree width of 2 or 5. And in general, increasing the tree width results in a more flexible partial plan. And so I think it did the best in the child snack and grid visit all again. But strangely enough, in about 2% of cases, increasing the tree width actually sent the algorithm into a dead end, and it results in a less flexible plan than if you'd given it a lower tree width. And also interestingly enough, this extra flexibility that you get from a higher tree width actually comes at not that big a computational cost. So in general, these final plans can be instantiated in about 200 milliseconds. That's just running on my laptop. And in a few cases, it just times out after about an hour. And those timeouts tended to happen more often with a tree width of 5 than a tree width of 2. So that's really the only difference. So in conclusion, partial plans generalize classical plans or partial order plans, but this comes at a bit of a cost of complexity. But we can still find islands of tractability, and we've got an algorithm there which allows a partial plan to provide flexibility while still remaining tractable. And there's a number of areas of future work, including better relaxation policies, so that's the choice of which precondition to relax at any point in time, as well as how to encode the causal structure as a constraint formula and various other things. Well, thank you very much. Thank you for coming. Thank you for listening.
Questions?
The tractable plans,
Yep.
they are quadratic to instantiate. Is it quadratic function of the plan length or what?
No, so it's a so when I say it's got it's k tractable is a common way of thinking about it. So a k tree width partial plan will be instantiatable in time n to the k. So if it's got a tree width of 2, it'll be quadratic, and that is relative to the input planning problem and the solution.
Yeah.
No, the plan, sorry. Yeah, the input plan.
And on examples that you were exploring, what would be the actual wall clock time in if you wanted to dynamically replan? You were saying it's applicable in real time, but what would it really mean?
Sorry, I missed all.
You said quadratic is not that bad now, so is it really for application of this in real time?
Sorry, quadratic is what?
You said quadratic is already good enough for real time.
Well, yes, I mean, arguably it's going to be quadratic. There are, so normally finding, so it takes a long time to generate a partial plan. So that can take up to an hour or so. But once you've got the partial plan, if it's, say, if it's got a tree width of 2, it's normally very quick to find an instantiation of that plan. So up to about 200 milliseconds.
Okay.
As I said, except for a few outliers where it can just time out completely.
Yeah.
Yeah.
All right, thanks.
That wasn't intentional.
So when you said that computing the partial plan based on the actual instantiated plan the planner has generated takes up to an hour, have you thought about not generating the fully instantiated plan at all? So I know it's a bit more difficult to do it, let's say, but there might there be any way to directly generate a such a partial plan?
Well, yeah, there is. But the only way that I can think of directly generating it is to use the modal truth criterion and just build the most relaxed possible plan. And the problem with that is that it tends to have it's just gigantic, and the tree width is huge, and it takes forever to instantiate it. So I also looked at other ways of doing it where you would sort of restrict the language that you use to express constraints in a way to kind of force it to be quadratic or something like this. But you tend to not really get much benefit out of these things they tend to be, the language is too restrictive to really express anything particularly useful.
I meant using the planner itself, modifying the planner itself to generate, so that the output of the planning algorithm itself is already a partial plan, because what came to my mind in the first lab was essentially what it looks like a symmetry,
So
somewhat.
yeah, I mean that's a good idea. So rather than relaxing an existing plan, just generate a partial plan. So yeah, I haven't looked into doing that. The other thing which I think is interesting is that depending on the actual plan itself, might achieve the same goal and be roughly the same length. Some plans can be very easily relaxed and others can't be. And I think, so I found that the plans being generated by the Madagascar SAP planner are really hard to relax in any way. The ones generated by like Fast Downward are quite easy to relax. And it could be down to the optimality. Maybe if a plan is already optimal, the resources are so tightly constrained, it's hard to relax them. If it's really suboptimal, there's probably lots of different ways you can adjust it. So I think future work, I might look into this. Yeah.
So I guess we have time for a short last question.
Behind you.
Okay, just thank you. There is a question from remote viewer.
Sorry, question?
Question from remote viewer.
Remote viewer. Oh, okay, yep.
Here, what if we wanted your planner to find a relaxed plan to begin with, instead of find a classical plan and then relax it?
Sorry, I didn't
Okay.
understand. Sorry. Yep.
Just read it. Read it out loud.
Yeah, so I mean that's
Read it out loud.
oh, okay. So the question was, what if we wanted a planner to find a relaxed plan to begin with instead of finding a classical plan and then relaxing it? Yeah, that's definitely another way of doing it. So that's often what's done in partial order planning. But so it's a difficult thing to do, and by doing it this way around, we can use a state-of-the-art state-space planner, for example, and then relax that rather than having to completely build our own planner. But it's definitely an alternative way of doing it. It's not something that I've considered. No, so I'm taking the similar approach as is used in, say, partial order planning, where, rather than constructing your own planner, you make use of the state-of-the-art existing planners and then relax the output.
Okay, let's thank the speaker again.